Welcome to AI Taper Podcasts. Today we're diving into something I think many of us in the field have been wondering about.
Absolutely. It's that constant question. Are large language models, hitting a wall? Are we seeing diminishing returns as they get bigger?
Exactly. We see benchmarks inching up slowly, and you start to wonder, but what if that's actually hiding something much more dramatic, like exponential progress, but maybe not where we've been looking?
That's the core idea behind the paper we're discussing today. It's titled The Illusion of Diminishing Returns, Measuring Long Horizon Execution in LLMs by Singha, Arun, Goel, and colleagues.
Right.
And it really offers a fresh look at LLM capabilities, especially for those really complex, multi-step tasks that are key for actual useful agents.
Okay, so for everyone listening who just needs the quick takeaway, maybe for your commute or that short break, here's the essence in under a minute.
Go for it.
This paper basically uncovers a pretty counterintuitive idea.
Yeah.
Really small, almost tiny improvements in how accurate an LLM is on a single step. Well, they can actually compound.
Right? Compound exponentially into massive gains in the model's ability to finish long, complex sequences of tasks.
And the reason LLMs often fail on these longer tasks, the paper argues it's mostly down to execution mistakes.
Yeah, not necessarily a failure in reasoning or planning. Even if you give the model the plan and all the facts it needs, it's like tripping over its own feet.
And there's this key concept they introduce.
The self-conditioning effect. Basically, the model sees its own past mistakes in the conversation history, in the context. And that makes it more likely to mess up again. It sort of learns bad habits from itself. And crucially, just making the model bigger doesn't fix this.
Okay, but here's the hopeful part, the game changer. They talk about thinking models.
Yes, models that use sequential test time compute, basically, thinking step by step internally before answering.
And these models, they actually fix the self-conditioning problem.
It seems so. They manage to execute much longer, more complex task sequences within a single interaction turn.
Wow.
And when they benchmark the latest thinking models, the results were pretty staggering. GPT-5, for instance, apparently executed over 1,000 steps.
1,000 compared to what?
Well, the next best was around 400 steps. So a huge lead. It really highlights, a potentially critical path for unlocking the real economic value of LLMs as agents.
Okay, so that's the snapshot. Fascinating stuff. Let's unpack this properly now. This isn't just about headline numbers, it's understanding the mechanics underneath, right? Yeah. Especially if you're building these systems.
Exactly. It's about why we might be seeing this apparent slowdown while underlying capabilities for complex tasks are potentially exploding.
So let's start with that central paradox. How can what looks like diminishing returns on standard metrics, like test loss, translate into these massive gains in real-world value or long task completion? This is where it gets really interesting, mathematically.
It really does. The paper lays out the mathematical foundation. You can see it visualized in Figure 2 and formalized in Proposition 1.
Right.
The core idea is, assuming you have a constant accuracy, let's call it P, for each single step.
Right.
And the model doesn't self-correct, then the number of steps it can complete, the horizon length h, before the overall success rate drops below some threshold s, is roughly ln(s).
Okay. Logarithm of success rate divided by logarithm of single-step accuracy.
Exactly. And what's fascinating, what the math shows, is that once that single-step accuracy P gets reasonably high, say above 70% or so, even tiny improvements in P lead to faster than exponential growth in H, the horizon lengths. It's not just linear, not even just exponential. It accelerates.
Wow. So small accuracy tweaks suddenly have this massive downstream effect on how long a task the model can handle.
Precisely. And this isn't just theoretical. It connects to things people are observing empirically. Like one study found that the horizon length for LLMs doing software engineering tasks seems to be doubling every 7 months or so.
Doubling every 7 months. That's rapid progress.
It is. And this paper provides a mechanism for how that can happen, even if the gains on those simple single-step accuracy metrics are slowing down.
So the real value, especially for agentic applications, comes from the length of the task chain the LLM can reliably execute.
Absolutely. If an agent needs to perform 50 steps correctly to achieve a goal, a model that's 98% accurate per step versus one that's 99% accurate per step, well, the difference in completing all 50 steps is huge.
Right. It's the difference between likely failure and likely success. So focusing only on short task benchmarks, like single question answering.
Might be giving us, as the title says, an illusion of slowing progress.
Yeah.
It masks the gains in sequential task capability.
Okay, that makes sense. It reframes the whole scaling debate. So if the issue isn't necessarily raw reasoning power, what is the bottleneck for these long tasks? The paper digs into the reason for failure, right?
Yes, they wanted to isolate execution ability. The common assumption is maybe the models fail at complex planning or accessing the right knowledge. They challenged that.
How did they test it?
They set up a really controlled experiment. You can picture it from figure 3 in the paper. The goal was to strip away the need for planning and knowledge retrieval, mostly.
Okay.
They designed a simple task, basically a loop, where the model has to look up values for keys given to it in an in-context dictionary, and then use those values to maintain a running sum, like a prefix sum calculation.
So very basic steps. Find a value, add it to a running total. The plan is simple. The knowledge, the dictionary is right there in the context.
Exactly. No complex reasoning needed, no searching external knowledge bases. They just varied the number of turns the model had to do this for, and also the turn complexity, which they called K.
K being the number of keys to look up and add within a single turn.
Yes, the number of simple retrieve and compose steps per interaction. The key question was, even with the plan and knowledge handed to them, can LLMs just execute this simple loop reliably over many, many steps?
And the answer was, I'm guessing from the paper's title, maybe not so reliably.
That's right. Result 1, execution alone is challenging, really drives this home. If you look at figures 4a and 4b, even powerful models like Qwen 332b, which got 100% on a single step of this task in isolation.
Perfect accuracy on one step.
Yes. But when asked to do it repeatedly, its accuracy for the whole task dropped below 50% in just 15 turns.
15 turns? That's surprisingly low for such a simple, repetitive task.
It really is. It strongly supports their hypothesis. Basic execution, repeated over time, is a serious challenge for these models, independent of planning or knowledge retrieval.
So what about scaling? Does throwing more parameters at the problem help with this execution reliability? What did result 2 show?
Result 2 was about the non-diminishing benefit of scaling model size, looking at figures 4a and 4c again. And here, they found something quite interesting.
Which was?
Larger models, like comparing the 32 billion parameter Qwen model to the 4 billion one, did maintain accuracy for significantly more turns. The horizon length scaled clearly with model size.
So bigger models execute better.
Yes, and importantly, the benefit didn't seem to diminish. The scaling trend for horizon length was strong. This is kind of non-trivial because, remember, the task itself doesn't get harder or require more knowledge for bigger models.
Right, it's the same simple loop, so why would bigger models be better at just executing it?
The paper suggests one potential reason could be redundancy. Larger models might have more internal circuits or pathways that can perform the same simple operation.
Ah, like having backup systems. So if one part messes up slightly, another part can still get it right, leading to more robust execution overall.
Kind of like an implicit ensemble effect within the larger model, perhaps, making the simple execution steps more reliable through sheer scale and redundancy, not necessarily through smarter reasoning for this task.
Okay, that's a plausible mechanism. And did they pinpoint where in the execution chain things go wrong? Is it the lookup, the addition, the state management?
They looked into that.
Yeah.
Figure 14 gives some clues. Individual operations, like just retrieving a value or just doing a simple addition, models handle those almost perfectly. The difficulty really ramps up with composition and state management. In that prefix sum task, the model have to both look up information and correctly update its running total, managing that state across steps. That's where errors creep in.
So it's the juggling act, keeping track of things while performing actions, that trips them up over time.
Exactly. Chaining even simple operations reliably and maintaining state seems to be the core execution challenge.
Which brings us back to the why. Why does performance degrade? We talked about context length being a common suspect, just too much information to handle. But the paper proposes this other idea.
The self-conditioning effect, yeah, they really wanted to tease these two potential causes apart. Is it just that the context window gets too long and confusing? Or is it something about the errors themselves poisoning the well?
How did they isolate that?
They ran a clever counterfactual experiment. They took chat histories from the execution task, but they deliberately manipulated them. They injected different rates of errors into the history that the model would see.
Ah, so they could feed the model a history with, say, 10% errors, even if the model itself hadn't made those errors originally.
Precisely. This let them see how the presence of errors in the context affected the model's accuracy on the next turn, separate from just the length of the context.
Clever. And what did result 3, self-conditioning causes degradation beyond long context, show? Figures 5A and 5B, right?
Yeah, two key things.
Yeah.
First, even with a perfectly error-free history, 0% injected errors, accuracy still dropped by turn 100. So yes, long context on its own does cause some degradation. That confirms the baseline issue.
Okay, so context length is a factor.
It is. But crucially, as they increased the percentage of errors injected into the history, the accuracy in the next turn got consistently worse.
So seeing past errors makes the model more likely to make a new error.
Exactly that. That's the self-conditioning effect laid bare. The model seems to implicitly learn from the errors in its context, making it drift towards a state where it makes more errors itself. It's a negative feedback loop.
That's a bit worrying, actually. It suggests models can sort of catch errors from their own past performance.
It does seem that way. And result 4, looking at figure 5C, adds another layer. Scaling model size does not mitigate self-conditioning.
So bigger models don't fix this feedback loop.
Apparently not. They tested several large frontier models, Kimi K2, DeepSeek V3, Qwen 3 235B. These models were much better at handling the pure long context issue. Their accuracy stayed near perfect at turn 100 if the history had 0 errors.
Okay, so scaling helps with general context degradation.
Yes, but even these big models still showed that same performance drop when errors were introduced into their history. The self-conditioning effect persisted regardless of model scale.
Wow. So scale helps with handling long, clean context, but it doesn't inherently make the model immune to being influenced by its own past mistakes.
That seems to be the finding. They draw an analogy to how a chatbot personality can drift over a long conversation, but here it's like the personality drifts towards one that makes execution errors.
Right. So the multi-million-dollar question then. Is there a fix? Can we break this negative cycle? Can we stop LLMs from essentially learning bad habits from themselves?
Well, this is where thinking models come back into the picture, and it's arguably one of the most exciting parts of the paper. Result 5. Thinking fixes self-conditioning.
Okay. How so? What did they find?
Looking at figure 6, the Qwen 3 models that were trained or prompted to use sequential thinking, like chain of thought, showed remarkably stable accuracy at turn 100, even when their context history was filled with errors.
Stable. So the error rate in the history didn't drag down their current performance.
Exactly. The thinking models seemed largely immune to the self-conditioning effect. They just kept executing correctly, regardless of the simulated past failures.
That's a huge deal. Why? What is it about thinking that provides this immunity?
The paper proposes a couple of potential reasons.
Yeah.
One might be the effect of reinforcement learning, if models are RL tuned specifically for task success.
Right, like getting the final answer right, not just predicting the next word.
They might learn to ignore distracting or incorrect information in the context, focusing only on what's needed to succeed at the current step. Another idea is that the sequential nature of thinking, where the model generates its reasoning step by step, allows for more independent processing. The authors noted that the thinking traces often didn't even refer back to prior turns, suggesting the model was reasoning things out afresh each time, rather than being overly influenced by the possibly flawed history.
Interesting. So it's like the thinking process insulates the current step from the contamination of past errors.
That seems to be the hypothesis. They also briefly mentioned that simpler context management, like just chopping off older parts of the history, also helps, presumably by removing the errors the model could condition on. That's in Appendix A2.
Makes sense. Less error exposure.
And they contrast this with other approaches. For example, they found self-verification, prompting asking the model to check its own work, was computationally expensive and often introduced its own errors. Not very effective. And things like parallel compute at test time, like generating multiple answers and taking a majority vote. Figure 10 suggests that only gives marginal gains compared to the power of sequential thinking.
So sequential, step-by-step internal reasoning seems to be the key to breaking that self-conditioning cycle and achieving robust, long-horizon execution.
It really appears that way based on these results.
Okay, this is fascinating. So thinking helps with reliability over many turns. But what about complexity within a single turn? Real-world tasks often need an agent to do quite a few things before interacting again, right?
Absolutely. That's the other dimension of long-horizon execution they investigated. How many steps, that turn complexity K, can a model handle reliably within one go?
How did they benchmark that?
They basically did a binary search. For each model, they tried to find the maximum number of keys K could process in that dictionary lookup and sum task within a single turn, while still maintaining at least 80% accuracy.
Trying to find the breaking point for single-term complexity. And what did they find first about models without chain of thought? Result 1 in this section, figure 7a.
It was pretty stark. Again, even the big non-thinking models like DeepSeek V3 or Kimi K2 basically failed when asked to do just 2 steps, K2, in a single turn if they weren't using chain of thought.
Only 2 steps. Wow.
Yeah, it really underscores how vital that internal reasoning before acting process is, even for seemingly simple compositional tasks. Without CoT, they hit a wall almost immediately when they're trying to do more than one thing.
Okay, so thinking is essential for multi-step turns too. Then they benchmarked the frontier models with thinking enabled. Result 2, figure 7b.
Yes, and this is where you see that huge performance gap emerge.
Lay it on us.
The standout was GPT-5, codenamed Horizon. It successfully executed over 1,000 steps, K1000, in a single turn while maintaining that 80% accuracy.
1,000 steps in one go. That's incredible complexity compared to just 2.
It really is. The next closest was Claude 4 Sonnet, which managed 432 steps. Still impressive, but less than half of GPT-5.
And the others.
Gemini 2.5 Pro, Grok 4, DeepSeek R1 were significantly lower, clustered around maybe 100, 200 steps, if I recall the chart correctly.
So a really wide spread in capability at the frontier for this single-turn execution depth.
A very wide spread. And another interesting point here, DeepSeek R1, which is RL trained, performed substantially better than its instruction-tuned sibling, DeepSeek V3.
Reinforcing that point about RL training potentially helping with robust execution and thinking.
Exactly. It suggests the type of training matters a lot for enabling these long horizon capabilities. It also highlights, though, that even the best open-weight models benchmarked here have quite a way to go to catch the top proprietary ones like GPT-5 in this specific capability.
Right. A significant gap still exists there. So takeaway 3 seems pretty clear then.
Yeah. Thinking models are crucial. They don't just fix the self-conditioning issue across multiple turns, they also dramatically boost the number of steps a model can execute reliably within a single complex turn.
It's like a double benefit for building more capable agents.
Precisely.
Okay, let's try and wrap this up. What are the main things we should take away from this deep dive into the illusion of diminishing returns?
Well, first, that headline idea. What looks like slowing progress on simple benchmarks might hide exponential gains in the ability to complete long, multi-step tasks. That's driven by the compounding effect of small improvements in single-step accuracy.
Right, the illusion part. Second, the bottleneck often isn't high-level reasoning, but basic execution, especially over many steps.
And a key reason for that execution failure is the self-conditioning effect, where models get tripped up by their own past errors in a negative feedback loop. Importantly, scaling model size alone doesn't fix this.
And this is the crucial but thinking models, the ones using sequential test-time compute like chain of thought, seem to break that cycle.
Exactly. They fix the self-conditioning and also dramatically increase how much complexity they can handle in a single turn, leading to potentially massive leaps in capability, as seen in benchmarks like GPT-5 hitting over 1,000 steps.
So connecting this to the bigger picture, what does it all mean?
It means that building generative models that maintain accuracy over these long horizons, long sequences of steps, whether across turns or within a turn, is absolutely fundamental. It's key for reliable agents, for complex simulations, for unlocking a lot of the promised economic value of AI.
It shifts the focus, doesn't it? From just making models answer single questions better to making them reliable doers over extended sequences. It's an output length and reliability challenge as much as an input length one.
Well put.
So for you listening, especially if you're building or working with LLMs day to day, what's the call to action here?
I think this paper really emphasizes the need to focus on execution reliability. Don't just assume a smart model can execute simple steps flawlessly over time. Embrace techniques like sequential test-time compute, encourage thinking, and develop strategies, whether it's RL tuning or clever context management, to mitigate that self-conditioning effect.
Yeah, those seem like critical areas for development if we want truly capable AI agents.
Definitely. And it leaves us with a pretty important question to think about, doesn't it? Yeah. This paper used a relatively simple arithmetic task to isolate execution. How do we take these insights about self-conditioning, about the power of thinking, and apply them to real-world agentic tasks?
Where the actions are more diverse, the dependencies are complex, maybe the state isn't Markovian.
Exactly. How would you design an aging architecture, maybe using these thinking capabilities, to prevent self-conditioning when the environment is dynamic and the potential errors are much more varied than just getting a sum wrong?
That's a great challenge to leave people with, designing robust agents that don't sabotage themselves over time in complex environments.
Lots to explore there.
Indeed. Well, this has been incredibly insightful. Thanks for walking us through this paper.
My pleasure. It's fascinating work with some really important implications.
Absolutely. Thank you all for joining us on AI Paper Podcasts. We hope this gave you a new lens through which to view LLM progress and challenges. We'll catch you on the next one.